Okay, let's look at the mechanism in general now. We've looked at a specific case where we're adding bromine, and just to tell you, if you've done the reading, you'll know that this is an oversimplified version of the mechanism, and we'll talk about the details of it in a little bit. What you will see the difference between the alkene reacting with Br2 up here and the benzene ring reacting with Br2 down here is that you need a catalyst for this to happen. The alkene is much more reactive as a nucleophile than benzene is. Benzene's unusually stable, and so you need a catalyst, iron tribromide, and that enters into the mechanism as well. But this is the basic mechanism here, the addition and the elimination. So if we draw this more generally, then if we just draw out a benzene ring here reacting with an electrophile, so this is our nucleophile, and this is reacting with our electrophile here, then the pi bond breaks and the electrons form a new bond to the electrophile where it has a positive charge on it. And again, the electrons are going away from this carbon. They're still attached to the top carbon there. And so then we have attached to the top carbon, so now we've broken this pi bond. In the top carbon here we have a hydrogen attached and an electrophile, and in the bottom one we have the hydrogen still attached and a positive charge, a carbocation, that is sitting there. And that carbocation is allylic, and there's resonance, and so that positive charge actually can be spread out over two other carbons on this ring. So that's step number one, which is breaking the pi bond, and so this is addition. And then step number two is reforming the pi bond. And getting rid of the hydrogen that was there. And so step number two is losing H plus and reforming the pi bond, which would be an elimination reaction. Okay, so this is the overall generic electrophilic aromatic substitution mechanism, which you need to memorize, and you need to think about how this compares with other mechanisms such as addition, electrophilic addition, which we saw up above. And so this first step in both of these mechanisms is exactly the same. The second step is different. Okay, let's have you draw the mechanism. Let's have you react benzene with an alkyl halide. So we'll just make a bromomethane there. Okay, so this is your nucleophile, this is your electrophile, and the first thing you do to think about the reactivity of this is to look at the atoms and assign partial charges. These two electrons in this covalent bond are shared, but not shared equally. Which atom are they closer to? They're closer to the more electronegative atoms, so that gives that a little bit of a negative charge, maybe a tenth of a negative charge, maybe a 20th of a negative charge. And since they're further away from this carbon, which is more electropositive, then that gives that a little bit of a positive charge. So here is the electrophilic atom. So pause the video and go ahead and draw this two-step mechanism showing the nucleophile attacking the electrophile, and then the second step, the elimination, reforming the double bond. Okay, let's see how you did. Hydrogens here, drawing them in to make sure that you don't forget where they are and forget how many bonds there are to the carbons. Pi bond breaks, electrons come up here, kick out the leaving group, and after the end of step number one, we have broken that pi bond, and we have a hydrogen here, a methyl group that has added, and a hydrogen here with a positive charge. And then step number 2, so that was addition, right? You're breaking the pi bond. And step number 2, you're reforming the pi bond, losing H plus in an elimination reaction. So addition and elimination. Okay? Same mechanism no matter what the electrophile. Let's have you do one more. Nucleophile, and we'll have you react it with the electrophile that forms after nitric acid and sulfuric acid react with each other. And that is this thing right here. Kind of funny looking thing, but when you have 4 bonds to nitrogen, right, it's got a positive charge on it, and the net reaction of this in the end is a nitro group is adding, and we know the nitrogen from a couple of videos ago is bonded to the benzene ring. So here's your new electrophile. Show the benzene ring attacking and appropriate bonds breaking and forming, and show the same 2-step mechanism that we are looking at for electrophilic aromatic substitution. So go ahead, pause the video, and draw out the mechanism. Okay, so again I'm drawing in these hydrogens just to keep track of them. I'm breaking the pi bond and attacking the nitrogen here, the positive nitrogen, and that would give it 5 bonds, which is impossible, so I have to break one of these pi bonds to make it have 4 bonds. Positive charge where the electrons went away from this carbon right here, and a hydrogen here, the nitrogen with a double bond to oxygen and a single bond to another oxygen where that broke, that pi bond broke and dumped the lone pair onto the oxygen there. And so we have our nitro group. And again, this is not an intermediate. This is what a nitro group looks like, or this is one resonance structure. The other one would be a double bond here and a minus charge there. But this is an addition followed by an elimination, and we're doing the same exact thing that we've done in the previous, in the general example, the previous example, and adding Br2 at the beginning. Getting rid of that hydrogen there. Putting in these bonds, and we don't have to draw out the nitro group like we did. I just wanted you to understand what the bonding and the charges look like. You can just write it like that. So again, addition followed by elimination. So this is the mechanism over and over again, and there are resonance structures of the intermediate, which is also important, and we'll come back to that and draw resonance structures and think about how that affects the charges on the ring and where the second electrophile will add. So, as I said, these reactions do not happen without a catalyst, and so we'll go back and look at 1 or 2 examples where the catalyst is involved. This is a generic electrophile here, just E+. This is the electrophile that has not been activated by the catalyst. You should be working on memorizing iron tribromide is the catalyst for this. And then this one actually is neither of the reagents. It's what forms after the catalyst reacts with nitric acid. But this is the 2-step mechanism that you need to have committed to memory.